Let's look at particle waves, and this time the de Broglie wavelength. So we know from Einstein's photoelectric effect and Compton's scattering experiment that waves behave like particles under certain circumstances. Louis de Broglie, as a graduate student, proposed that all moving matter has a wavelength associated with it. So by all moving matter, it doesn't mean just waves, but also particles. So particles have a certain wavelength associated with them. And the value of that wavelength is h over p. Just as a reminder, this equation was derived from relativity, where E was mc squared divided by square root 1 minus v squared over c squared. Momentum was mv divided by square root of 1 minus v squared over c squared. So there's various ways of doing this, but let's say that we solve for the square root of 1 minus v squared over c squared here, and that would be mc squared divided by the energy. Plug that into the momentum equation and have P equals mv divided by mc squared over E. And we can cancel out the mass, so that is EV divided by c squared. For particles moving at the speed of light, then V is equal to c, so the momentum is E over c. And we remember that energy was h times frequency divided by c, where frequency was c over lambda, and that's divided by c. So we can cancel out the c and end up with P is equal to h over lambda, rearrange that, and end up with this de Broglie wavelength. So the confirmation for this came from experiments done by various physicists. Davison and Germer were two Americans who scattered a beam of electrons off of nickel crystal, and they observed X-ray-like diffraction. So again, X-rays are high-energy photons. And then an Englishman by the name of George Thomson observed electron diffraction. Now, a little bit of trivia here. There are a lot of people on this list. Einstein won the Nobel Prize for Physics in 1921. Compton won the Nobel Prize in 1927. De Broglie won it in 1929. Davison and Germer did not. They won some other awards, and Germer actually decided that rock climbing was an interesting thing, so he did that for like a quarter of a century. And George Thomson won the Nobel Prize in 1937. Another piece of trivia is that George Thomson is the son of J.J. Thomson, who won the Nobel Prize in 1906 for the charge-to-mass ratio of an electron. A more recent experiment that was done was sending a beam of electrons through a double slit. So basically performing Young's double slit experiment with a beam of electrons rather than a beam of light. And the same type of interference pattern was observed on a screen from these electrons, from the beam of electrons. The conclusion from all of this is that other particles can also behave like waves. It doesn't have to just be electrons. So while the electrons behave like waves, they actually are waves of probability. There's a certain probability of finding a particle at a certain location. And that probability is proportional to the square of the particle's wave function. So each particle is going to be assigned a certain wave function psi that the probability is proportional to. Schrödinger embraced this concept, and he and Heisenberg pioneered a new branch of physics called quantum mechanics. So they developed some of these wave functions and something called the Schrödinger's equation that explained how particle waves behave. Heisenberg is also famous for the uncertainty principle, which says that one cannot predict the momentum and the position of a particle with absolute certainty, or one cannot predict the energy and the time of the particle with total certainty. So there is this relationship between momentum and position, energy and time, and that's greater than or equal to Planck's constant h divided by 4 pi.